Well, good afternoon and welcome to our seminar on knowledge elicitation and geopolitical reasoning under extreme uncertainty. My name is Stefan Conradi and I'm the managing partner of Bayesian USA. A little bit later, a colleague of mine, Dave Abisher, will join us. He's running slightly behind schedule, but you'll have a chance to meet him after the break. So let me share with you what's on our agenda for today. We're already in the middle of the introduction. After that, I'll talk about our methodological motivation, and that is we want to reason, and yet we don't have any data. Which brings us to the topic, well, what is reasoning after all? How do we formally reason about a problem domain? Which leads us to the rationale for Bayesian networks. And then I will share with you an introductory example. Some of you may have already seen that, but I think it is important to, just to kind of as a warm-up exercise and to become familiar for those of you who haven't seen Bayesian networks yet. Here at the bottom of the screen, now you can see it. Here we have the credentials for the Wi-Fi system here in this building, and then also there is the link for the GoToMeeting that you may want to join to see the screen a little bit better. It's entirely up to you. The Wi-Fi connection you will ultimately need for our knowledge elicitation exercise in the second part of today's seminar. So the first part really will be mostly me talking and just showing PowerPoint presentations and examples from BayesiaLab. That should take approximately 60 minutes, after which we will have a coffee break. I should also point out I'd like to take a photo at the coffee break, but from previous seminars I know the spooks among you are sometimes concerned about appearing in photographs, so I'll give you a fair warning so you can hide your face or do something to protect your identity. So after the break, and by the way, I should say you should feel free at any time to grab coffee out in the break area, so we can keep this fairly informal. Anyway, after the break, in part 2 of the seminar, we'll get into our proper case study. And the theme for today is territorial disputes in the South China Sea. And I have not advertised that topic simply for the reason because it is just a case study example, so I didn't want people to get attracted on the subject matter per se. It's just I'm using this as an example of how we can reason about the subject matter, and I'm not going to elaborate on the problem itself. So more specifically, the problem we will have at hand is a missing US submarine and how we can reason about its whereabouts and how to, what efforts should be undertaken to recover the submarine, etc. And for that, since we have no data about that, rather, I mean, as you can imagine, a submarine that's somewhere hiding in the depth of the ocean, when we have no communication whatsoever, in that case, we literally have no data and still need to reason about this particular problem domain. So that's where we bring in the Bayesian expert knowledge elicitation environment, where we together will think about, well, given that it's this day and we haven't heard from it in so many hours and we have not received an emergency signal, what's the probability that it is in hostile waters and that we can't launch a rescue mission, etc. So we'll try to bring together what we might know about this domain, bring it into a Bayesian network, and then that can help us make the appropriate decision to optimize the decision, how we should go about. Should we launch a rescue mission? Should we not? Where should we do it, etc. So that first part, or for the most part, this will be again me talking, but then at the end we will have an exercise in which you can participate where you will literally be able to contribute your knowledge. So, and that should take about 2 hours. Now, let me start off with some disambiguation. I will talk about many concepts related to Bayesian. This will pretty much be every other word I say. So Bayesian, that's our company. BayesiaLab, that's our product that you will see in action. But really all this revolves around the paradigm of Bayesian networks. So that will be the focus of today. Now let me tell you a little bit about the background of our organization. Bayesian, our company, was founded in 2001 by 2 professors in the field of artificial intelligence research, Dr. Lionel Jouff and Dr. Paul Monteanu. They were originally teaching, or at that time, they were teaching at the University of Rennes in northwestern France. And they were doing work with Bayesian networks, but it was at the time very tedious to practice with Bayesian networks because you had to manually code everything. So they wrote this little utility, this tool for their own research purposes, but then very quickly other researchers noticed this technology and wanted to adopt it as well. So they decided to start a company, called the company Bayesian, and over the nearly 20 years since, this little utility has grown into a fairly comprehensive software platform, a portfolio of software packages. You might actually say it's kind of an ecosystem consisting of desktop software, web applications, and then finally our set of APIs. But today we'll just focus on 2 areas. One is BayesiaLab Professional, that's the core application, and you will see Biki, our Bayesian expert knowledge elicitation environment. So, even though we're still a fairly small company, we have a broad spectrum of customers all around the world, and you will recognize most of these logos. Our single largest customer is Procter & Gamble. They use BayesiaLab in the context of marketing science applications, but then we have the Army, NASA, the Navy, wide range of applications, financial institutions, pharmaceutical companies, technology companies like Intel, Microsoft is another customer, market research firms like Nielsen, GfK, TNS, Ipsos. It's really a very, very broad spectrum. And I'm mentioning that to highlight really how universal Bayesian networks are in what you can do with them. Whereas today we will use them without data. We will use them just for encoding our knowledge and working with that. In many cases, many of our customers go the opposite way. They just have data and they perform knowledge discovery from that data and then want to interpret that. They want to learn from the model that is generated through machine learning. But as I said, we won't do that today. Now, one thing I saw, people are starting to take pictures. You're more than welcome to take pictures, of course, but all the slides, everything you see today, including the networks we build, you will be able to download at, I will send out an email with download links, and if everything works, we'll even have a video recording, or rather a screen recording plus the audio. Now, today we won't have time to go into any detail about what Bayesian networks are. I mean, that's an entire seminar in itself. To learn more about the basics of Bayesian networks, the math behind Bayesian networks, I recommend that you download our book. It has really become quite a popular document. It's been downloaded thousands of times. And I must say, though, this book is based on BayesiaLab version 5.4. Okay, no problem. Okay, so we're now on version 8. We've just released BayesiaLab 8, so you'll see some discrepancy between the book and the screenshots or the screens you will see today. However, we're working rather frantically on the next edition of the book. So hopefully early next year, that book will be ready and it will be once again available for free download. Now, one more thing I would like to mention, and that is we're always giving out credits for participating in the seminars. And while you may think this is perhaps a little bit... while you may think this is a bit of a marketing gimmick, it actually turns out to be relevant in the sense that we know that there are quite a few recruiters out there who are looking for people who are familiar with Bayesian networks. Just the other day, somebody called and said, hey, can you tell me and point me in the direction of people who have some familiarity with Bayesian networks? So it certainly won't hurt posting the seminar credits, this micro credit, to your LinkedIn profile. So during the break, if you can come see me, I'll scan you in, then I know you were here, and then you will automatically receive that credit. So, and I would like to keep this fairly casual, so please interrupt anytime, protest, feel free to disagree. We can have a conversation about anything I bring up, and you have microphones in front of you, so we will all hear you. So you will not go, we won't miss your comments. So for those who just arrived, I should mention one more time, we have coffee and cookies out to your left. Just go towards, as you go out this door, walk down the hallway to your right, and you will see a kind of a break area with coffee and cookies. So feel free to help yourself at any time. All right, let's get to our motivation, which is no data. Of course, this is a little bit the opposite of what everybody's talking about. Everybody is talking about making data-driven decisions and big data, and it remains pretty much a hyped up topic, and it's quite obvious. I mean, we don't need to explain why data is so relevant and so important, and there are countless quotes about why data is so relevant. This one perhaps is one of the most popular ones. In God we trust, all others must bring data. Supposedly, Edward Deming said that, but the attribution is actually disputed. But now, what do we do if we don't have any data about a problem domain? Now what? What happens then? And now this is confirmed to be said by Edward Deming. Without data, you're just another person with an opinion. And well, that's unfortunately what we have. For our problem domain today, this is as good as it gets. What we believe, what our opinions are about the problem domain, that's all we have. However good, however bad, however biased it is, that's what we have to work with. So now, because of all this talk about big data and data science and machine learning and artificial intelligence, we're almost conditioned to believe that, well, unless we have data and lots of it, really there can't be any proper scientific inquiry. This is really a major, major misconception. We need to realize that even without any data, as humans, we have so much knowledge, whether qualitative or quantitative, about so many aspects of real-world problem domains. And so our objective now is to capture that in a formal way, to reason about it in a very explicit, in a very scientific way. And that's where most people kind of get hung up. It's like saying, well, if we have just opinion, if we just have your opinion and your opinion, how can we be scientific about it? Isn't it just he said, she said? So before we go into how we can embrace Bayesian networks in this context, I want to propose a framework. I want to propose dimensions of reasoning. So, and perhaps starting off on this topic, whenever we mention reasoning, or I should perhaps back up and phrase it differently, one topic that is most often brought up when it comes to reasoning is logic. Probably what is most associated, the close relationship between logic and reasoning. And that relationship certainly makes sense, but logic really isn't sufficient for reasoning. And I'm quoting somebody else who said it so nicely. Classical logic has no explicit mechanism for representing the degree of certainty of premises in an argument, nor the degree of certainty in a conclusion given those premises. What this means is logic really isn't enough as we reason. So let me kind of map this out in this way. If we think about the strength of an argument from weak to strong, really only at the outer limit at the very right we have formal deductive logic. For the rest, everything else to the left of the, or not on the far right of this spectrum, we're dealing with probabilistic reasoning. We have to use that. And you can imagine in our everyday life, there are many situations where we are all over that spectrum. You know, we say, I see a dark cloud, so it will probably rain. And that's probably sort of on the stronger side, as opposed to when you listen to pundits on TV who say, well, given that President Trump said this, therefore they infer something else. You know, that could be on the very, very weak side, and so on. So we're dealing with the whole spectrum of reasoning, and very often what has been a problem in the past is that we were kind of clueless how to deal with reasoning on that broad spectrum. We knew what to do, we know what to do, how to handle logic and to formally deal with it. Our computers can beautifully deal with it, but the spectrum to the left, that is problematic. So this spectrum I want to use as our z-axis in our coordinate system for dimensions of reasoning. So on the left we have probabilistic, and then towards the right we have deterministic arguments. Well, roughly 2,000 years after Aristotle, this problem has been solved. In Reverend Thomas Bayes, who was just a hobby mathematician really, he came up with the method, the computational approach for updating our beliefs in a premise and a hypothesis given new evidence. So this is obviously known to all of us now as Bayes' rule or Bayes' theorem, and it's perhaps one of the most famous formulas in the history of science. And even though it is so powerful, it hasn't really become, it is still not in wide use. But let me just emphasize that. Bayesian inference is important because it provides a normative and general purpose procedure for reasoning under uncertainty. So this is really it. So whatever you do in terms of reasoning, when you reason probabilistically to do it right, you need to, however you arrive at it, it needs to match the results from Bayes' rule. Now, the problem is that intuitively we humans don't do that very well, or I need to differentiate a little bit. When it comes to reasoning from cause to effect, intuitively we get it mostly right. The problem happens when we try to reason from effect back to the cause. That is the huge challenge. That's when fallacies happen, because we can't intuitively use Bayes' rule as we reason backwards, as we perform diagnostic reasoning from an effect back to the cause. And this has huge implications. It has huge implications that we can't get it intuitively right, and that we're not using Bayes' rules explicitly, that we're not using it for updating our beliefs. And perhaps one of the biggest problems is that the fact that in courtrooms, this remains practically unused. So really, in the area where it's probably most important that we get probabilities right, and that is the probability of guilt of somebody who is accused of having committed a crime, in that area, the rules of probability and Bayes' rule remains mostly unused. There have been initiatives to address that, but reality shows us that it's really not, or current practice shows us it's not used. And, excuse me?
Question?
Yes.
How do you characterize the difference between Bayesian techniques and fuzzy probabilistic techniques?
Well, I think there's a lot of overlap between them. Well, fuzzy logic is a type of reasoning, is a type of computation that is, I think, sort of a very pragmatic approach. Comes out of computer science to implement something, whereas Bayes' rule is very much theory-driven, that has sort of universal application. So if you reason correctly with fuzzy logic, if you want the result to be correct, it has to match Bayes' rule. Now that's the kind of the fundamental natural law. And then fuzzy logic and algorithms in that context would have to arrive at the same conclusion. One of the challenges with Bayes' rule, and we will see that very shortly, is from a computer science perspective, it has been difficult to apply that when it comes to using lots of variables in complex domains. Until a few decades ago, it really wasn't possible to perform inference in complex domains. So there's another area where I had anticipated, or I had expected, that Bayes' rule would have been used almost universally, and that is the whole field of the intelligence community. Interestingly enough, that's really not the case. When I started looking at what's out there in the public domain about the intelligence community using Bayes' rule, there was actually very little. And however, what I did find were references to why it is not used. And that I found very, very surprising. Here's another quote from somebody's, I think this was a master's thesis. Due to the highly mathematical nature of Bayesian decision analysis, many users, and that means intelligence analysts, will feel uneasy trusting the resulting assessments. And that kind of, I found rather troubling, that just because it is difficult to use, even though we recognize it is correct, but because it is difficult to use and sometimes counterintuitive, we are not using it. And that's what we want to overcome today. Indeed, some of the results we see today will be counterintuitive. We will not be able to solve that with a pencil and paper approach. We will not be able to replicate this with, let's say, an Excel spreadsheet. But that can't possibly be the reason to dismiss it. If somebody has objections to Bayes' rule or objections to certain statistical methods, then by all means come forward to it, but don't reject it because you think it is too difficult to use. So anyway, so that will be, again, that's our first dimension, but now this is our formalism with dealing with our first dimension. So really, for the most part, Bayes' rule applies, and only at the outer limit, at the far right, that's where we have logic. So that's what we need to realize. So let's get to the next dimension. And that dimension, I was prompted to think about it that way by a paper by Galit Shmueli. She's an Israeli researcher who's now teaching in Taiwan. And in 2010, she wrote a paper about to explain or to predict, in which she pointed out really how many scientists conflate the purposes of models. They may build predictive models and then interpret them in an explanatory manner, or conversely, build an explanatory model, a structural causal model, and then use it for prediction purposes. And in either case, it's not right. Even though a explanatory model should have some predictive purpose, very often a black box predictive device may actually predict much better than a true structural causal model. On the other hand, just because something predicts well doesn't mean anything about what really the true underlying structure is of a problem domain. So you may have variables from a problem domain, you may pick them up, put them into a model that comes up with good predictions, with really good forecasts. The fact that certain variables end up in this predictive model doesn't mean anything what their true causal role is, what their data generating role is in the real world. So that will be our second dimension of reasoning. This will be our x-axis, the axis of model purpose. On the left, we have association correlation, referring to prediction and description, and then on the right-hand side, we have causation, explanation, simulation, attribution, and optimization. For today's problem domain, we will actually use the entire spectrum. So we will use really this entire axis. We will utilize both ends, if you will. So now about the question, where do we get models from? What is our source? This will be our y-axis. Now, in the past, until big data became a thing, really most models came out of theory. We, as researchers, we hypothesized about a problem domain, then perhaps wrote down a formula, collected data, and then estimated parameters. But nowadays, of course, we have so much data, we can, through clever machine learning algorithms, we can automatically generate models just from data without any theoretical knowledge. And what I hear very often is there is this belief that, if we just have enough data, the data will speak for itself. We may not need any theoretical knowledge any longer. That's a major, major fallacy that we need to be very careful about so we don't fall into this trap. But let me explain specifically what I mean with that. Let me now put together our x-axis of model purpose and y-axis of model source. And let me now place machine learning and artificial intelligence onto this map. So I will use this as our map of analytic modeling and reasoning. So I'm putting machine learning and artificial intelligence in here, and you will not be surprised that it's sort of on the upper end of the y-axis, because after all, machine learning is driven by data. But more important really is understanding where it sits with regard to the x-axis, because models that are learned from data, automatically generated from data, they really can't extend beyond this kind of barrier that I drew on this map. The right-hand side, causal considerations are entirely off limits for strictly machine learned models. Why is this an issue? Well, most of the research questions we have, are about reasoning, why, how, what to do, who is responsible. And those are very, very clearly causal questions, which we cannot address with black box models by themselves. So for today, it is very important that we distinguish between the left-hand side and the right-hand side here. And in a few moments, we will also see why we need something like Bayesian networks as a formalism to distinguish between these two sides. I'm using algebra here, kind of fake algebra, to indicate what the difference is. On the left-hand side, we're really trying to build models that help us infer values based on what we observe. Given that we see the clouds are dark, we believe it will rain, which is totally different than inferring something based on an intervention, an action that we undertake ourselves. So for algebra, it's just y equals f of x. We cannot distinguish between seeing x and doing x. In algebra, it's all the same. Using Bayesian networks and graphs, that allows us to distinguish between these two types of inference. This will be absolutely critical for today. That's why I keep reiterating this. When somebody refers to data-driven decisions, that's kind of a fallacy in itself, because when we talk about decisions, it's mostly about taking an action, intervening in a problem domain, as opposed to data-driven is mostly about observing things, having observed things and inferring on that basis. So therefore, that's an oxymoron, really. Anyway, so how can we deal with this now? How can we, aren't we stuck now? Well, there's a way to overcome this barrier. And please don't get me wrong, I'm not saying machine learning and AI is not very useful. It's hugely important. I mean, just think about all the things that are now possible thanks to AI and machine learning and big data. This is all fantastic. Think about our cars that can drive by themselves and our phones that can understand what we're saying and all these great things. But now the question is, how can we bring that together? How can we use machine learning and AI for reasoning, for scientific inquiry? Well, the gap here that we need, or the gap that we need to close, we can close with our domain knowledge, with bringing in, contributing our own human domain knowledge. And now you may say, well, how does that work? How can we take data generated knowledge and the opinions we have in our heads? Well, that's where Bayesian networks come in, because they can really cover the entire spectrum. So we can take machine learned knowledge. In fact, we can machine learn Bayesian networks directly from data, but we can also put in directly our knowledge. And that will in fact be what we will do for the rest of today. We will not do any machine learning, we will just straight put in our beliefs about a problem domain into a Bayesian network. But if there were data, if we had some data source, and very often it's a mix of everything. We have a little bit of data about that part of the problem. Here we just have opinions. Here we have a whole bunch of experts who know something. What we want to do is bring that all together. And very importantly, Bayesian networks also facilitate probabilistic reasoning. So we can, yes?
Just before we leave that subject, when someone asks you, and you distinguish between machine learning, artificial intelligence, and Bayes reasoning understanding, would you intelligence supports Bayes region or Bayes networks, or is Bayes network an extension of the underlying area of machine learning and artificial intelligence?
Well, I've very much simplified that, and I put machine learning and AI into that upper left-hand quadrant. And that was really a oversimplified presentation, because Bayesian networks are, in a way, a type of AI. They represent, they are a form of artificial intelligence. They're just not a form of artificial intelligence that we hear about as much today, because most of the things, whenever you hear about AI these days, when it's about your car, about your phone, all the cool stuff that is happening, for the most part, that refers to deep learning and neural networks. That's really what is common practice, or really the big thing in AI. But you're absolutely right. Bayesian networks really aren't a distinct thing, but rather they are a form of artificial intelligence, but it's something that most people often forget about. I just wanted to distinguish between pure machine learning, which is strictly data-driven, as opposed to Bayesian networks that can be both driven by data and driven by domain knowledge.
Thank you, Professor. So following this up, if you could also distinguish whether the data and domain knowledge are the same. Could you just clarify?
Well, and there's a big distinction here, because data is just, and when I refer to data, I'm mostly referring to observational data. I'm just collecting, how many people walked through the door, and their attributes, demographics, and from that I can machine learn a model. I can establish relationships, but I couldn't really derive anything about what causes what. I couldn't generate a causal understanding how attributes of all these individuals about whom I've collected data, how all these interact, and what causes what. As opposed to a causal model, domain knowledge. I'm just trying to think of an example. Here's an example. There is a correlation between body height and hair length that applies across all cultures everywhere in the world. The taller you are, the shorter your hair. Any simple algorithm, any model building exercise would pick up that correlation, and would be true. So if I had somebody's height, I could predict the hair length, or the other way around. But what I cannot discover from that is that is not a causal relationship. The causal relationship relates to gender. If you're male, or by virtue of being male, you're taller, and typically have shorter hair. By virtue of being female, you're shorter and also have longer hair. That is domain knowledge, that we could not discover from data directly. Now in today's example, we don't have any data at all. Excuse me? It's an observation. Yeah, and observations can be fine. Sometimes it's just all we want to do is predict. We don't really need to know, is it, like for instance, if you were Amazon and you had either, you have some bits and pieces of information, you don't care whether it was, hair length that causes gender and gender that causes hair length. You just need to know, well, given that I observe this, I need to show them that, or they're probably a shopper for that. That's just prediction. But if you want to intervene in a domain, if you want to take active steps about engaging in a problem domain, then you need to have this underlying structural knowledge, how it works. And that's what we're going to try to capture today. And that can come from data. That's the key point. So the paradigm of Bayesian networks, the term Bayesian networks was coined by Professor Judea Pearl, who's been teaching and researching at UCLA since 1970. And he had originally invented Bayesian networks for what I just mentioned. They're so capable of distinguishing between associations and causal relationships. They are the formalism that allows us to really represent our causal understanding of a problem domain. And so what I'd like to do now is, or one more thing I should mention, for quite a long time, Bayesian networks remained in the background. So probably many of the devices you have, the software programs you have, some of them contain Bayesian networks as a kind of implemented as an algorithm. But what we want to do is use them explicitly as a direct research tool. We want to use them as an aid for our thinking and reasoning. So we want to bring them to the surface. And that really has been the focus of our work now for many years. So let me now describe all the great things about Bayesian networks. So I will, as I said at the beginning, we don't have time to really go into the math behind them, which is remarkably simple. So don't be ever scared of thinking of Bayesian networks as something very complex. It is not. But I would just want to touch now on all the cool things you can do with them, or all the cool attributes. First of all, Bayesian networks are great for representing high-dimensional domains. So if you have domains with hundreds and thousands of variables, they can be very compactly represented in a Bayesian network. And in a Bayesian network, you don't have to distinguish between dependent and independent variables. You can simply take the domain, all the variables, and start building it. Just thinking about what relates to what. You don't need to distinguish between this is X and this is Y, and so on. Closely associated with that is the fact that in a Bayesian network, you can perform omnidirectional inference. You can reason from any node to any other node. And that's one of the key properties we will use as we're reasoning about the missing submarine. Bayesian networks are non-parametric. We don't have to specify a functional form. We can have any kind of relationship between variables. They are probabilistic, meaning we can work with things like I probably observe this, or this is the probability of, or this is the degree of my belief, my expectation, and so on. I can encode causal relationships. I think Bayesian networks are very intuitive because you can read them like an influence diagram. You can simply follow the arcs, what causes what, and they're very nicely scalable. So you can really go from 2 nodes to 10 nodes to 1,000 nodes, and yeah, you don't have any constraints in that regard. So let me just illustrate this one point, and I leave all the detailed slides in here in the presentation that you can download. I just wanted to show this to highlight this omnidirectional inference. My background is in engineering, so I always come back to a mechanical example. So here is a set of gears, and hopefully you will agree with me that if I provide some input torque on the left gear, then that input propagates through the set of gears and drives all the other ones. But I can also do this the other way around. I can enter an input on the right, and then it propagates backwards. Or I could start in the middle, or what have you. Well, I could have 2 sources that contribute power to the system. That's exactly how a Bayesian network works. I can provide inputs anywhere and I can read out wherever I want. So I can see how information flows through my network. Very, very powerful. Okay. Let me just perhaps touch on that. And we could talk for hours about every aspect. Let me just touch on one of the key motivations for embracing Bayesian networks, and I want to illustrate that with Newton's second law of motion. The way you've probably learned it in high school is like this: force equals mass times acceleration, which is interestingly not the way how Newton originally wrote it. Well, of course, he wrote it in Latin, but if you were kind of deciphering his Latin, what he was referring to is he was talking about acceleration, mutationem motus, the change of motion, is proportional to v motrici impressae, but it's not just proportional or equal, but rather he is referring to this impressae, the force that impresses. So what Newton was referring to was a causal assignment. So the force causes the acceleration. But we can't really tell that from this equation, because an equation we can solve. We could solve for mass, for instance, perfectly valid transformation, but here there's no causal interpretation possible. It could be causal, could be not causal, but we can't see it from the equality sign. So that's why Bayesian networks are so powerful, because there I can be very explicit about what's causal, what is not causal. So let me now start off with a quick, let me very briefly introduce how BayesiaLab, our software, fits into this. So we've taken this mathematical formalism and translated it into a research software, into a research workflow, so that scientists can either take expert knowledge or take data, machine learn from data, and then bring both of that together. And then once you have the Bayesian network, you can analyze it, simulate, optimize. In the most general sense, use it for decision support. That's exactly what we want to do today. We want to decide, well, where should we search for the submarine? Given the conditions that we face, should we even search for it? So now, as I mentioned earlier, BayesiaLab has been under development for nearly 20 years. We just released BayesiaLab 8, and that's what you will see as we go through our exercises. That's the software platform now that allows us to encode Bayesian networks, to learn, to edit them, to perform inference, all the way to actually optimizing decisions. So let me very quickly go through this simple example. And it is really quite simple, but you'll be surprised how much interest this has gained over time. In fact, Judea Pearl, in his latest book, The Book of Why, has picked up our example and actually devoted like half a dozen pages to speaking about it. So I was quite happy to see my name quoted in this bestseller. So let me tell you about this example that Judea Pearl picked up. This was my story about traveling from Singapore to the US. At the time when this real story took place, there was no direct flight between Singapore and the US. So I had a connecting flight, and I had to change planes in Tokyo and Narita. So here's the story in detail. So I checked one bag in Singapore, and as soon as I checked it in, there was an announcement: there is a typhoon coming into the South China Sea, and we'll be talking a lot about the South China Sea throughout this afternoon. But here was simply a natural event. Because of the storm, because of the typhoon, all flights out of Singapore were delayed. And I arrived in Tokyo Narita with like a 4-hour delay or something. I forgot how much it was exactly. It was a significant delay. So, and I was concerned that I wouldn't make my connecting flight that would take me then to LAX. So I raced across the terminal, got to my departure gate, and then I made it, of course, but my question then was, well, will my bag make it? And the gate agent was very confident. She said, oh yeah, I'm pretty sure, we're very efficient here in Japan, given that you had like at least 20 minutes of connecting time, there's an 80% chance that the bag will make it, okay? So I get on the plane, fly to LAX, and of course I'm a bit concerned because 80% is not certain. So that left me with some discomfort. So I arrive at LAX. I see how the bags are being unloaded. So they're all coming down the chute onto the baggage carousel. And as time passes, I still do not see my bag. So my question is now, well, after I've now waited for 5 minutes, what's my probability that I will still get my bag? So what do we need to do? So really what I need to do, or what we need to do, is we need to infer, given what we observe, what's the probability that I will still get my bag? Given that I observe I haven't seen it in the first 5 minutes. So what do we need to do? We need to encode our knowledge, and this is now entirely in parallel what we subsequently will do with the submarine. Here it's perhaps just a slightly more familiar experience because we've all been there. In fact, I was there again yesterday when I landed at Reagan Airport. So what's the probability that we will get our luggage given what we've observed so far? So I will leave PowerPoint real quick and switch into BayesiaLab. Let's see whether that works. This is our slide for our network for later. So here is my blank screen. What I want to do now is encode a network that will help us to reason about this problem. So what are your thoughts? What do you think? What should we capture about this problem domain in order to reason about whether we'll still get our bag or not? What are the things or let's perhaps start with, what are the things we can observe about this problem domain?
Is it flight delay?
Well, the flight we have, that already happened. So the flight has landed. The question is, was my bag on that flight on which I just arrived? So,
It's only been 5 minutes.
it's been 5 minutes. I've been watching the bags coming down the chute for 5 minutes. I have not seen my bag. So how should that update my belief?
Do they send out premium bags first, or were you on a premium ticket or not?
Yes, that's absolutely correct. This is kind of in the expanded view of the model. We start with the very, very core. Yes, Ross?
Was the agent that told you was 80% lying to you?
Well, now you're getting into sort of we're not talking about spies yet that intentionally try to mislead you.
When they say 80-20, it's usually a higher percentage that it will make it.
Yeah, so perhaps they are overly optimistic.
90-10.
Yeah. Okay, so I propose that we start with a variable that we can observe. Are bags still coming down the chute? Absolutely. That's one. I would like to start. Now I'm getting entangled in all these cables here. I would like to start with one of the very few variables that we can directly observe, and that is my bag on the carousel? That's the one thing I can observe for sure. So I'll call this variable my bag on carousel. And let me make this larger. So What else can we observe in this context?
Passengers on the flight.
Passengers on the flight, we could, but it's again in the expanded model.
If there are 10 people.
That's obviously different, absolutely. I'm looking at the most simple version of this. How many? That's a good one too. You're already in the big model, and anyway, that's what I'm referring to with the scalability. So as you have more thoughts about the domain, you can add this. You can sort of make it, as you think about it, as you discuss the problem domain, you can expand the complexity. But I want to start with the very, very core. So I would argue we can see my bag on carousel. And the other thing that we can observe is time. We can simply look how much time has passed. But what is the variable that we want to infer? What do we want to, because these two we can see, but there's one variable that we cannot observe, and that is my bag on plane.
Just to work that out, okay.
Yeah. So we want to infer my bag on plane, because that's kind of in the cargo hold of the plane, and we can't see that. So my question to you now is, how are these variables related? What causes what? We now need to think about our causal understanding of how this works, and then encode that causal knowledge, and then we can use it for reasoning. So what are your thoughts?
When you say my bag on plane, you mean it's still on the plane?
No, it's the variable that represents whether or not my bag is on the plane. So we don't.
Made the flight, or will it still on the plane?
It is basically the placeholder. It's the variable x that stands for presence on the plane. But we don't know that. We're trying to infer that.
I think that what he's getting at is if the bag's sitting on the carousel, it's not on the plane, but it did make the flight.
It did make the flight, yes.
So is the variable that made the flight, or it's still on the plane?
Okay, very good. Now I understand. It's really, it made the flight. It was on the plane. Yeah. Was or still is. That's the most precise way of. Thank you. So how are these now related?
There's some kind of distribution, but if the time is 0, then it's not going to be in the carousel.
Yeah. Mm-hmm.
If it's some time in the future, if the time is long enough, and it's not in the carousel, then it's never on the carousel.
Aha, very good. So what you have basically said is time is a cause of my bag on carousel. And what you've also implied is that the bag being on the plane or having been on the plane is a cause of my bag ultimately arriving on the carousel. Yeah? Yeah? So that is the structure. That's our causal understanding of how the world works. Now we need to specify some.
It's just a little bit different. I mean, it's binary. The bag on plane and bag on carousel, a binary relationship. One infers the other.
Yes, but it's not deterministic because, as the gentleman pointed out earlier, if we're in minute, if they just started unloading the bags, then no bag is on the carousel. In the fullness of time, all bags should be unloaded. So we now need to encode your thinking about that function, that delivery function, in how are the bags coming off the plane down the chute on to the carousel. So let's do that now. Let's now add some quantities behind these variables. And perhaps let's start with the easiest one, my bag on plane. I'm opening this node. This is a binary node. It can just be true and false. Perhaps I can make this larger. On my other computer, I can. Does this work here? It does work. So I can now enter my a priori beliefs about whether the bag was on the plane or not. What did the gate agent tell us? 80-20. So I can take this as if I believe it, I can say 80-20, or perhaps we should say 90-20, whatever we make of that. I'll stick with that original statement. I say 80-20, and now we have specified that first node. Time is a little bit easier, or rather, first of all, time is not a binary variable, rather it's kind of progresses in intervals. And here I'm making a simplistic assumption. I'm saying that the total time horizon is 10 minutes, or rather from minute 0 to minute 10. In 10 minutes, all the bags should definitely be unloaded. You shake your head, it's perhaps not. Excuse me?
They are not that efficient.
They're not that efficient, except when you're in Singapore. Oh yes, they're all there in 5 minutes.
But you're right.
I mean, yeah, exactly. Now I'm on my. I just for the example. Sorry, I'm now just getting the chair tangled up in the cable. Ugh, it's getting worse. Okay, if I get strangled here, please come rescue me. So if I turn blue in the face, then it's because of this dumb cable. So yeah, I just chose the 10 minutes for convenience, but that's obviously an assumption that may or may not hold. But one thing that is certainly true is that time progresses in even steps. You know, there is no time interval that's more probable than another one. Time progresses evenly. So I can simply apply a uniform distribution here. So now comes the interesting part. Now I need to specify the function or something that tells us how the presence of the bag on the plane affects the appearance on the carousel. And I would argue that this table is actually very easy to fill out, at least the top part. The top part now tells us here on the left we have my bag on plane, false and true, and then time. So what is the probability for the top part of this table? I would argue it all has to be false, because if the bag was not on the plane, it can never appear on the carousel, right? Yeah. How about if the bag was on the plane? You have to find the distribution. Yeah, and here I would argue perhaps they unload the plane evenly and deliver it. So I'm making this highly simplifying assumption that the probability of the delivery, of having delivered the bag, increases in 10% increments.
It could get lost in LA.
Of course, it could get lost in LA, which I haven't modeled here. So I've omitted that part if there is a chance. You know, so perhaps that's just the maximum should be 95%. But then I should make that an explicit assumption. So let me close this. Now we have a fully specified Bayesian network. My question to you now is, it is 5 minutes. What is the probability that we still get our bag? What's your gut feeling? So, how much? 40? 50? 60? 80? Who said 80? Ross said 80? 70? Any other offers? 60 or 70? Okay. So we kind of have a fairly broad spectrum here. Okay. Very precise. Okay, let's answer this question. Now we have all smart people here in this room, and yet we have a fairly broad distribution of answers. So let's get to the true answer. So I'm now switching from the modeling mode into the validation mode. Now we can take BayesiaLab to perform inference. So I'm bringing up all my variables in the form of monitors here on the right-hand side. Hopefully you can see that. And now I can simulate. It is minute 5, and I have not yet seen our bag on the carousel. So given that it is minute 5, we have not seen it on the carousel. The probability of my bag having been on the plane is 66%. So your guess was perhaps the best one of all. So now what about how about minute 8? What do you think about minute 8? What are the offers for minute 8?
I think it's easier to imagine, you go up, you can go up within probability and determine like
88%?
It's likely that there's a better chance that the bat was on the plane. If it wasn't on the plane at all, then of course it'll go down.
Okay, so what is our expectation in minute 8? I haven't seen it in minute 8. What's
looking for whether it was on the plane or not?
Yes.
That's just
12%,
8% longer.
The longer you wait, the more likely. Okay, close to 80%? 84%? Any other bids?
The longer you wait, the less likely it was on.
Less likely?
I was expecting to be less than.
Less likely? So what's your number? Ah, 15? Okay, let's find out. 50. Okay, so, okay, let's check. The answer is 44%. Okay, we can now keep playing this game, but a good way to use BayesiaLab in this context is to just analyze this automatically. And I'm simply plotting a function of how the probabilities evolve over time. And this I find quite fascinating, is even though all our assumptions that we've entered are perfectly linear, this response curve that shows us the probability is far from linear. So we kind of can see a very clear inflection point, or rather, I don't know what we can call it an inflection point, but here at roughly 7.5 minutes, the probability drops below 50%. But the thing is, even though this is such a simple problem, we can't really do that easily in our head. We can't picture it. We can't compute it in our head and reason about it intuitively. That curve, I bet you nobody in this room would have plotted the curve in that particular fashion. And the problem is also, even if I gave you paper and pencil and said you have the rest of the afternoon to calculate that, it's practically impossible unless you're either a genius or a PhD in statistics. I certainly couldn't do it.
Well, because you got to count all the ways that it can occur, all the ways that it can occur. You got to have that straight.
Yes,
That's
but
hard to do.
that is hard to do.
Looking at the table,
It looks like a sine curve or cosine.
Actually, I'm not sure it has any underlying function. I don't know what the functional form would be. The reason why this is so tricky is we are actually performing intercausal reasoning. We are reasoning from one cause via the effect back to the other cause. And so we need to apply Bayes' rule twice. The first one is still fairly easy. The second one, that's the tricky one. Applying Bayes' rule in that way intuitively is just practically impossible. And so this was a trivial example. Now we will use this in the second part of the seminar. We will use the very same thing about reasoning about where is the submarine. except there are many, many more variables in play where it just gets infinitely more complex. Not complex for us in terms of encoding our knowledge, infinitely more complex for computing the answer. And that's where Bayesian networks and Bayes' rule really shine.
Stephen?
Yes?
I can understand where if the bag is not on the plane, it will cause the bag not to be on the carousel. But I'm unclear about the counter reasoning. I may be wrong, but maybe I'm not saying right. My bag on the carousel doesn't cause anything to the bag on the plane, right? Is that correct?
So my bag on carousel is the result. Yeah? But that's the point about Bayesian networks. Even though the arcs point from time to my bag on carousel, from my bag on plane to my bag on carousel, that's the causal structure. In a Bayesian network, I can reason in both directions. So I can reason from my bag on carousel back to my bag on plane, even though it's in the opposite direction.
This is working. So I think that curve is similar to the ROC that we see.
It actually looks like that. It looks like one, yes. Interesting. It would be interesting to explore what the relationship is. So we're running slightly behind schedule. You have screenshots of everything that I've shown in the slide deck. So I suggest we take a quick coffee break. But as promised, if you don't mind, I'll take a quick photo of the group. Okay, let's now get to our case study. We're now entering the realm of submarines. And what I should mention, and I said it at the very beginning, I didn't want this. Hold on, I think you still can't hear me. Can you hear me now? Okay. As I said at the beginning, I don't want this to make this a political seminar debating the claims in the South China Sea. So everything I'm talking about in terms of adversaries, enemies, conflicts, hostilities, this is strictly for methodological illustration purposes. So when I'm referring to the communist menace, that's just looking at it from a very technical perspective, so it has no innuendo whatsoever. So also all the numerical values I'm showing are purely fictional, and all what I'm going to describe is highly simplified just for illustration purposes. So let's look at this domain. You're probably all familiar with the disputes in the South China Sea. Here we're zoomed in into that part of the world. You may know that the South China Sea is one of the busiest shipping routes in the world. I think a third of all global transportation travels through the South China Sea. Most of China's exports travel through the South China Sea. But unfortunately, there are many territorial claims that collide in this area. China, in fact, claims most of the South China Sea, but Taiwan has claims, Indonesia, the Philippines, Vietnam, Malaysia, Singapore, Brunei. They all claim portions or certain islands in this area that's outlined here with the red line. It's known as the 9-dash line, even though I wasn't able to replicate the 9 dashes, but that's specifically the area that China claims, which is also claimed by many other nations. So, as you can imagine, that area has huge strategic importance for China. And there are two areas in particular that I want to point out, and that is Hainan Island, that's undisputed Chinese territory, and then a set of islands, the Paracel Islands, that are just south of Hainan Island, that are kind of one of the many islands that are claimed. There are the Spratly Islands, there are I mean, there are literally hundreds of rocks and little islands that are claimed by different nations. And what I should also point out, China has been very active in expanding some of the rocks. The basically islands that were barely islands, they were just like rocks that appeared on low tide, and they've been building them, fortifying them, expanding them, land reclamation projects, and so on. But that's not the topic here. This is simply background to our discussion. I should also point out that China has built a nuclear submarine base in that area at the very southern tip of Hainan Island in the Yalong Bay. And that's where we're going to zoom in now. Now we're looking at the very, very southern tip of Hainan Island. And this is the area where this naval base was set up. It's quite a significant structure that includes docks for large surface vessels, but it also has docks for submarines and has underground tunnels where they can literally, or are believed to be able to accommodate dozens of nuclear submarines. So that's the highlighted area. Now we're going to zoom in a little further. So this is all from just Google Earth. There you can actually see how many, like 6 submarines simultaneously sitting at that naval base. And zooming in a little bit further, here for instance you can see a Jin-class submarine, one of their intercontinental ballistic missile capable submarines, or that's what these submarines are built for. They have a dozen or so ICBMs loaded onto them, and there they sit. And not surprisingly, it's a very convenient position there in the South China Sea. So what I find so fascinating, that somehow you would expect China being as large as it is, that naval base would be hidden somewhere in some remote area that is totally inaccessible to the public. But in fact, it's on one of the most popular beaches on Hainan Island. And just like in easy walking distance, there's a Holiday Inn, there's a Ritz-Carlton, there's a Marriott. And in fact, from all those vacation resorts, you can directly look across the bay and see the nuclear submarines sitting right there. So you may sit there on the beach, sipping your daiquiri, thinking about traveling home, and just in 2 miles from you, you see this nuclear submarine whose missiles could reach home much, much sooner than you ever could. So it's kind of somewhat ironic. Anyway, that's the situation. The submarine base, or the entire naval facility, outlined here in red, and we're now looking out onto the South China Sea. Okay, and that's the area we want to reason about. Now imagine we have a mission, and this is all fictional. We have a Virginia-class submarine, one of the modern submarines, nuclear-powered attack submarines that the U.S. Navy has. And such a submarine is supposed to patrol the sea trials of a new Chinese Jin-class submarine, like one of those we just saw parked in plain view. And they're obviously building more and more of these, and so the Navy obviously has an interest in monitoring their whereabouts and where they go. And of course, this new submarine is based at Hainan Island. So our fictional mission is about tracking, or is about monitoring the area, patrolling this area, and trying to track down, or kind of monitoring the Chinese submarine. So the area we're talking about is roughly 240 nautical miles by 240 nautical miles. And there's kind of an oval course. That's our planned route for our submarine. So the mission, our fictional mission, is 4 days in duration. And as you would imagine, as you're getting close to your adversary's territorial waters, you want to avoid all communication so that they can't detect you. In the same way, we want to track down the Chinese submarines, they want to track down us. So here's the proposed course of our submarine. And of course, it's the commander of the sub can deviate from that course given the operational requirements. But we can divide this mission area into 4 quadrants that I'm pointing out here. And looking at the planned schedule, it would take 4 days. And here I've labeled kind of the segments that the submarine would travel on each day. So basically, after 4 days, the submarine would be back in its starting location and would be able to communicate again. But en route, there would be absolutely no communication for obvious reasons. So that's the first thing we need to know. And now let's look at some of the considerations. There are also kind of environmental considerations we need to look at. And this route, this planned path, covers an area where you have the edge of the South China continental shelf. So roughly half of the route is in very, very shallow water. Some of it below, some of it as low as 150, 200 feet. And then as you come to the edge, then you really kind of fall off a cliff and you're into really, really deep water, thousands and thousands of feet deep. So that's the diagonal line here. So that's something we need to remember. So shallow water and deep water. And then, of course, perhaps most importantly, we're traveling through waters of different territorial claims. So one is totally undisputedly Chinese territory. That's when we're close to Hainan Island. Nobody is disputing that is fully Chinese, no dispute whatsoever. But then as we travel through some of the other quadrants, we're going into areas that are Chinese claimed territory, but where there's perhaps less of a certainty about what would happen if we were to venture into those waters. And the US Navy has been quite adamant about freedom of navigation exercises through some of these areas, just to say, hey, these are international waters, and we're going to travel through them, and we don't care what the Chinese claim. So again, I don't want to get into are these legitimate rights or not. I'm just saying we have different areas in our mission area with different degrees of territorial claims or different degrees of certainty. So that's the backdrop. That's what we have to consider. So our boat now goes on patrol. It departs, and obviously we wouldn't expect to hear anything from that submarine. But of course, after 4 days, as it completes its mission, we would expect a report that says, okay, we're done, and here's what we saw. But now we don't hear any signal from the submarine after day 4. And of course, that's reason for concern, because now we wonder, well, what happened? What could have happened in that area? You may ask, well, where is the submarine now? What happened? Was it detected? Was it detected by the Chinese? Did they perhaps capture it? Was there some hostile military action? Should we go search for it? And if so, where should we start with the search? What is even the chance of a successful rescue? I said earlier, there's very, very deep water where it will be practically impossible to launch a rescue mission. And then there are very shallow waters, but then some of the shallower waters are on the Chinese side. So there are all these things that are floating around. should be floating around in our heads. Among them also, how long could the crew survive? If something happened, how long could they last? If they're at a depth of 500 meters, at close to the crush depth of the hull, how long can they last? And then, of course, if you launch a rescue mission, what are the political implications? Because as you launch a rescue mission, and this is the actual undersea recovery vehicle of the US Navy, that thing is pretty obvious. If you show up in, 20 miles off the coast of Hainan Island, they see that you're there and they know, well, they're trying to rescue a sub. What is the sub doing there? That shouldn't be there, and so on. So it has all kinds of implications, or there are all kinds of considerations we need to bear in mind as we decide on, well, should we launch a search and rescue effort, and where should we launch that? Or do the risks outweigh the potential benefits of rescuing this submarine? So, what do we need to do? What we need to do now is construct a model that helps us decide. So what I'm envisioning is a model that can help us understand, think, reason, predict, and simulate. And here I'm showing this mechanical model of our solar system. Why am I showing this? Well, because I think we can all look at this model, at this mechanical model, and we can immediately see how it works. What it means, the position of the planets relative to each other. We can see the dynamics, how they move against each other, etc. Of course, that model is fairly easy to build because we have tons and tons of data. We have observed planets for centuries and could compute all their paths and how they move against each other very, very easily. Of course, we don't have that because that submarine was on the first mission of its kind. And even if it had done something similar before, it's probably not on a predetermined mathematical curve, but rather has to respond to operational requirements. But what I want to do now is take our thinking about, well, what are the drivers of the submarine's behavior? How would they react given certain environments? When would they send an emergency signal? For instance, would they send an emergency signal if they were close to Chinese waters? And perhaps if they were just in disputed waters, would they send an emergency signal, as opposed to would they send an emergency signal if they were close to the mainland, and so on. So we want to basically build all these considerations into a single model so we can then reason about and optimize our decision. So, and again, I'm repeating myself, we have no data. This is other than what we generally know about the dynamics and the behavior in this domain. We don't have data on, how many times have the Chinese sunk submarines out of the last 1,000 conflicts. That doesn't exist. It has not happened. And just to put it in the context of our previous map of analytic modeling and reasoning, we're now at the bottom. We're just reasoning purely based on theory. We cannot machine learn anything here. We just have to take what we know about the problem domain and encode that. And we have to cover the entire spectrum, both association, correlation, and causation, because very, very importantly, we need to make a decision. We need to send or not a rescue vehicle into potentially hostile waters. So this is very clearly an intervention. This is not just predicting whether the crew is still alive. Of course, that part we need too, because we need to infer, given of what we know, is the crew still alive? Can this vessel be rescued? So that's all that we need to do now. But very, very importantly, as we encode our knowledge, we're not going to encode how we reason. So we're not building a decision tree. Not at all. Rather, we need to encode the dynamics of that domain, how that domain works, how the world works. That's what we need to encode in this particular structure. So let's get started here. And again, please interrupt me at any time if you have questions. So this is the proposed approach towards decision making. This is what I'm proposing here as our workflow. So we start off with encoding our knowledge of how we think the variables relate to each other, similarly to what we did with the missing bag. Now it's just a lot more serious. Yeah? So now it's not, is the bag on the plane? It's more like, are our sailors still alive? You know, where are they? And so on. So we need to encode our knowledge. But beyond just qualitative knowledge, we need to elicit probabilities very specifically. Well, in our where's my bag example, we did it kind of casually and made some assumptions. But now, obviously, it's a bit more complex. And we will need to combine the knowledge of everybody in our group. So we will assume you guys are the experts, and we will elicit your thoughts about these different conditions. Well, what if we were in Chinese waters? How would the Chinese react? Those things, those opinions we must elicit. Then, of course, we need to provide utilities and costs. Perhaps there are some things that are easy to elicit, like perhaps, well, how much it costs to send a rescue vessel. But then others are much more difficult. Well, what is the cost of a potential military conflict with China? I mean, we could go crazy and say, well, this could be the start of World War III. You know, how do you value that? How do you put assessments on that? And then finally, and that's in a way the easy part, once we have encoded our dynamics, assigned our probabilities and costs, the decision making and reasoning about all these probabilities, that's well beyond what we can do in our heads. That's where inference algorithms and the computing supports comes in very handy. And here with BayesiaLab, we will see it's simply a click of the button to figure out, well, what's the optimum decision under a certain set of circumstances. But importantly, we will separate these, because very often when you are in a decision-making body, in committees, in task forces, and so on, as you debate with your peers, very often these different assessments get all commingled, and I've seen this in boardroom conversations of Fortune 500 companies, where discussions drift all over the place, and consequences and assumptions and get all mixed together, and it's very difficult to really have a high quality discussion. So that's why we want to separate this in our approach. And yes?
Can you go back to the slide? How does this technique, these approaches, how do you handle sensitivity analysis where gaining new information on parts of the model are more valuable than other parts?
Exactly. That's exactly what we can do. Even though we have no data, by virtue of having our beliefs encoded, we can then say, well, what should we know? How valuable would a certain information be? How, like, let's say, if we had an emergency signal, how would that change our decision? Or how would it change our decision if we received an emergency signal yesterday as opposed to having received it a day earlier? So we can then do even though it's all based on our knowledge, the collective knowledge encoded into a Bayesian network allows us to do this kind of sensitivity analysis. That's that's exactly where we're going with this. Now, I'll briefly mention this now, this knowledge elicitation environment. This is our technology that helps to formally elicit opinions of a group of experts. from you guys. And I'll talk about this in detail as to how that works very shortly. So let me now take you step by step through our approach. Let's start with the model construction. So the starting point is, oops, what was that? PowerPoint just crashed. Hold on, and so PowerPoint is back up. Hope it stays that way. So here we are. We would now talk as a group about, well, what variables, just like we did with the bag example. Well, how do these things relate to each other? After that, once we have established the causal model, then through our Biki server, through our Biki tool, we would elicit everybody's opinion individually about the relationships in this domain. You know, then, and this is very important, and I'll speak to that shortly, to keep everybody's opinion independent. We'll talk about biases from groups. Next step would be to collect utilities. You know, what's it worth? You know, or what's the cost to us or the risk to us if China captures a submarine? You know, not just the loss perhaps of a submarine, but them having access to all the technology that is on the submarine. That could be a huge cost to us. So then finally, once we have everything, we can use BayesiaLab for optimization. But let me now talk about this knowledge elicitation. This is really important. Or why we're going in the direction of collecting the opinions of many as opposed to simply relying on individual experts, perhaps. This has been widely documented. Whenever you ask individuals, they have biases. We all have biases in pretty much everything that we assess in all our decision making. And many of these biases have been documented. There is one very good book that lists many of them. It's the book by Kahneman and Tversky, Judgment Under Uncertainty, Heuristics and Biases. And there are things like confirmation bias, framing effect, availability bias, and so on. Many, many different types of biases that affect all of us. And so one obvious thought is, well, let's go beyond the individual. Let's talk about groups, and perhaps we can compensate for our individual biases by going to groups. Well, now we have different types of biases. Now we have groupthink, group polarization. We may have, if we had a debate here about this, and Christina may totally dominate the discussion that nobody else dares to speak up. It's like, and then perhaps a person with less experience in this particular domain wouldn't dare say anything because she has so dominated the discussion so far. So we want to avoid it, we want to overcome that. So the idea now is, that was the driving force behind the Delphi method, take the positive from the groups, such as the knowledge from a variety of sources, and then at the same time prevent the negative. That was the motivation why the Delphi method was originally invented by the Rand Corporation. So it was developed to achieve a reliable opinion consensus from a group of experts. The backdrop, or one of the thoughts was, or let me actually go to this slide first. That was the situation at the time. This was in the early days of the Cold War. Rand Corporation wanted to figure out a way how to establish the objectives of the Soviet arms buildup by estimating what they thought the Soviets were thinking about what it would take to destroy America's defense industry. So they were basically asking experts, about what do you think the Soviets believe that they need to wipe out America's defense industry? And it's obviously there is no data on this, especially not back in the 1940s and 1950s when satellites imagery wasn't available yet and so on. So they were basically trying to think, put yourself in the shoes of a Soviet military planner. What do they have in mind? What would they think they need to destroy us? That was the backdrop. And that exercise was performed and done with a lot of effort, and in retrospect, it turned out to be quite accurate, and that you could write a book about that whole topic. But of course, there were critics of this method, and that kind of kept saying, well, this couldn't be nearly as good as data. Of course not. Of course, it would be better if we could do a survey of the Soviet military and count their tanks and their missiles. But the problem is we can't. So the alternative is either we throw up our hands in despair and say we can't possibly know anything, or we try to make the best of our situation and bring together the thinking of our experts. And that's what this method is about. Let's bring together the thinking of many individuals who have familiarity with this domain and bring it together into a model. So what we're going to do beyond the Delphi method, the Delphi method at the time in the 1940s and 50s was basically getting to a single number. It's like, how many ICBMs do they think they need? Whereas we want to take it to, well, what is our collective reasoning? We want to take our logic, the logic that we have in our heads, and bring that together into a unified network so that we can jointly reason and explicitly reason. So let's get to our model construction. Let's encode what we know. So let me and here you just thinking back about our missing bag example, you can see how that takes a while. As we think about it, as we think about what variables are involved, this can be a very tedious process. And when we do this with our clients, that is often like a 2, 3, 4, 5 day project working through a problem domain. So, but let me now simulate this and kind of take you through the steps as to what we could think about in this context. So I would start with encoding what was the plan, what did the Navy plan in this domain? Basically, what were we thinking as we set up this patrol? And let's encode that. Now, then let's think about the dynamics within the mission. What could happen? How could an incident come about? What would happen in case of an incident? What would happen on the boat? Would they send an emergency signal? Now, there we can, in some cases, we may simply draw on protocols, on operating procedures, and emergency procedures that may be very well defined. Some other things we may just have to guess. But importantly, as the potential incident is underway, it's a black box to us. We may know about what they would do in certain circumstances, but we cannot observe what they actually do as it happens. So if the submarine floods at a given point in time, we cannot watch that. So the only thing we can observe is signals from the mission. So we can see something like, well, we've received an emergency signal. And one thing we need to bear in mind, and I didn't elaborate on that, and many of you will know that, communication with submarines is difficult anyway. And in most cases, it's easier to communicate from a command center to the submarine as opposed to the other way around. To really get a message from a submarine, it basically needs to be either very close to the surface or actually drop in an antenna that floats to the surface to send off a signal. I think there are a number of innovations in process. So perhaps today the US Navy may be further along. There are all kinds of IARPA, DARPA projects in progress about improving submarine communication. But for decades it has been a major issue that actually getting a message from a submerged submarine to a command center is very, very difficult. Anyway, so that's one thing we need to bear in mind, that we may get few signals even if all goes well, and that we may get no signal whatsoever if there is actually an incident. And based on that, we have to take a decision. We have to, like, let's say we have not heard from them in 6 days. What should we do? And that impacts, or what we need to consider is, of course, what we must consider is how likely will our search and rescue effort be successful. But then, on the other hand, we need to consider how will the Chinese respond to it. You know, will they consider our search and rescue effort perhaps as a hostile activity? And we need to assign all these utilities. But if we now look at this flowchart, it's not really a flowchart, it's more kind of a conceptual diagram. We need to realize that the top part is really about observational inference. We're trying to reason from what we observe back to what might happen. We have not heard from the submarine, therefore we infer that some days ago an incident may have happened. So we're reasoning from effect back to the cause. On the other hand, we're reasoning forward about we're evaluating different decisions. What will happen as a result of them? You know, what will the Chinese do? And so on. So we're reasoning upstream and downstream. So let's do that now. Here's our mission area again for reference. And I'm simply starting now to encode certain relationships that I hypothesize about. I would argue, for instance, that the position of the sub in my quadrants is related to the overall timeline. That there is a causal relationship that the further along, or as time elapses, our submarine is further along on the planned course. Yeah? How exactly, what it was, we can perhaps either have that plan, have the specific probabilities as to where it should be when, or when it should be where, but perhaps given the operational requirements that may actually deviate. So we have to perhaps ask another submarine commander and say, hey, what would you do? Where would we be? And encode that. And then, of course, we would have to go continuing further. I said position is a function of timeline. And furthermore, I would say the depth is a function of the position. As I said a little while ago, we have very different ocean depth in different parts of our mission area. So we have very shallow areas, and then we have very deep water. So we need to encode what is the probability of certain depth given certain positions. And then we need to elicit or think about in what territory are we given the position where we are on our mission. And in some cases that can be deterministic, because we say we know for sure that is Chinese territory, but perhaps as we approach the Paracel Islands, you know, who knows what they would enforce as their territorial border. So the qualitative relationship is very straightforward. The exact numerical values, those we would have to elicit from experts. So here's our network so far. Strictly qualitatively, here we have the overall timeline This is what we had earlier for our missing bag. We said our time horizon is 10 minutes. Then here we have our position that would describe how far along the boat is as a function of elapsed time, what the depth is given the position, and the territory given the position. So, and then we have to think about how likely an incident would be as a function of different conditions. And here I'm proposing, I think, the location of the submarine is certainly a driver of an incident, and perhaps the depth. And I would argue, strictly qualitatively, in shallower waters, an incident is much more likely because there is other naval traffic, patrol boats. In shallow waters, there's always a much greater risk of collision, as opposed to in deep water, where you can simply go deep and avoid all shipping lanes and so on. As I said earlier, in some areas of the South China Sea, it's just like 100, 150 feet deep. It would be very difficult to go deep enough with a submarine to avoid all traffic. So that depth is certainly a driver of potential incidents. And then territory, because we need to bear in mind there could be a hostile interaction, as we've observed in the past with Soviets, where they've been chasing American submarines and we're certainly threatening them. So that could be a driver here as well. So, but how? We have to gather that from the experts. So that was one side. Now moving on to the next one. I said we cannot directly observe the incident because we have radio silence, perfect radio silence during the mission. The only thing we can really observe is the boat back or not? Have they reported the completion of their mission or not? Just like what we did earlier with the bag on the carousel. Is it there or not? We cannot see, was it in the cargo hold? We can only see whether at a given point in time the bag has arrived. This is what we can observe about the boat. Have they reported back or not? And here in this case, we're reasoning about, and of course the interesting case is only if the boat has not returned, given that it has not returned by a certain time, what can we say about the probability of an incident? So that is something we need to encode. And then finally, we need to put that together and think about what happens with the crew. What is the probability of the crew condition given that a time progresses after, or that an incident happened? And of course, in most cases, we would think that the incident can only have a negative impact on the crew condition. Given that we're dealing with a submarine, we also need to consider that probably if something happens, the longer we wait, the greater the risk to the crew. Yeah? So we need to encode that. So we need to speak to an expert and ask, well, how long will they survive at a given depth for a certain time after an incident? And I'm sure that has been very well researched, and many folks in the Navy have a good understanding of that. So that's what we would have to encode here. And then we keep going. And one thing is certainly an emergency signal. But that emergency signal is a function of many causes. One of them could be, well, are they actually alive? Because if there was such a catastrophic incident, they may no longer be in a position to send an emergency signal. Time is probably an element as well, because perhaps if the nuclear reactor shut down and they're running on their emergency batteries, then they may not have the energy, quite literally, to send out an emergency radio signal. Or given that they are in hostile territory or potentially hostile territory, they may say, hey, we're not giving away the location of our boat, given that we're 5 miles off the shore of Hainan Island. You know, we will not give that away. And here we would have to encode the reasoning and the conditions that a submarine commander may encounter. So, yeah. But as I said, most of the variables we just described and the interactions we cannot observe. The only thing we can observe, and again, just in this simple case, we can observe what's the overall timeline, how far along are we in the mission progress. We know when they left, we know when they should come back, we know whether or not they came back, and we know whether or not we've received an emergency signal. Those are the only things we have, and from those observations we have to reason backwards on everything that's in the black box. And perhaps somebody may say, hey, don't we just do that intuitively anyway? You know, as we talk about it, as we think about it. And yes, of course, when you listen to conversations among those who reason about the problem domain, all these dynamics come up. All this will be we're not inventing new dynamics. We're not inventing or discovering new relationships in that problem domain. The problem is that traditionally, you certainly can't put that together in your head. Even if you're Garry Kasparov, the world chess champion, you could not simultaneously compute all the probabilities and reach the correct conclusion given your assumptions. So that's where fallacies come in. And you could see how, even with the simple bag example, we had a pretty broad spectrum of guesses. Now let me show you how much more complex it would be in our problem domain here. Whereas in our bag example, there was one influence path that we had to compute from time via bag on carousel, bag to bag on plane. Was one influence path that was way beyond our mental capabilities to compute, to correctly update the probabilities. Now, in this highly simplified example, there are 16 influence paths that we would have to simultaneously compute in our heads to infer any of the variables that we can't directly observe. And it's just intractable. Actually, until like 20 years ago, about 20 years ago, it was computationally, even for a computer, intractable to calculate all that. Let me give you an example here. I've described the structure, all the dynamics, and this is obviously very, very simplified. The real world has many more variables and many more interactions. I'm showing one of the 16 influence paths to crew condition. If we wanted to infer, is the crew still alive or not? And let me just trace that. We can observe time. Given that they have not come back, we would have to reason this way, that way, that way, that way, that way, that way, that way. So there are like 8 steps where we would have to apply Bayes' rule to update our belief correctly about the crew condition. But it's just one of 16. So we would have to compute this one along with all the other 16 influence paths in the same way. So yeah, only a genius or superhuman could do this. So yeah, we just can't do this in our heads. So, but that was just the first part of it. This was just reasoning from the signals we have back to the mission. What what happens? What's going on the submarine? What is their condition? You know, what possibly happened? Now we need to look at the second part of it, and that is the causal inference. What happens based on our response? And that's now a decision for us to make, because we're in charge. We have to, yes?
Can you share any thoughts on the considerations and the trade-offs of either linking or decoupling those two parts of the reasoning process, whether we benefit or lose by linking the inference about what the incident was with the decision on what to do about it?
Yes, I'm arguing we can't delink them, because at the end, if we just stop here, let's say, we now have our model, it's not that we have a fixed output. It's not that it says our crew is alive and they are in quadrant 2 and the incident happened 3 days ago. No, what we have is we have distributions. So we have a distribution across the quadrants, across the territories, across, there's a probability of them being alive, and so on. So we need to now, instead of taking a fixed single point value and moving forward with it, we have a distribution of all the conditions that we need to use to base our decisions on. So that's the key thing, and that's what often goes wrong in real world decision making. Give me a number. Tell me what is your best guess where they are. And providing that single point estimate for the location and for all that, that in itself is a fallacy, because that, unless you, of course, you know it, they can only be in one place. But that's a very, very unlikely condition. What you would have distributions across all these variables. And you may know they're more likely to be in quadrant 1 than in quadrant 2. But in quadrant 2 is a hostile territory. So even though, you know, there are all these things coming together, so we need to simultaneously maintain all the distributions as we go forward.
So then you're seeking to carry your quantification of your uncertainty about the incident into your deliberation.
Absolutely.
So rather than selecting responses that might optimize any particular outcome, you want one response that best accommodates your expected value.
Exactly. That's exactly what we're doing here now. So here's now the decision to make, and that of course is, you know, we either do this or that. That's really the only part where we don't have probabilities, because that's under our control. We have to say we don't search, or we search in quadrant 1 or 2 or 3. There, it's either or. That's black and white. But then, of course, what is not black and white again is, well, how are Chinese going to respond? And by the way, this acronym PLAN stands for People's Liberation Army Navy. So you'll now see this acronym appearing quite a few times. And even given the decision to launch a search and rescue mission, there's only a certain probability of finding them. And given where we find them, there's only a certain probability that we can rescue them, which again depends on depth, you know, because the rescue module that we have only goes down to 500 meters at most. So there are all these things, and so of all these potential outcomes, we have to take their distributions and their utilities and basically compute the expected value across all these possible outcomes, responses, etc. And then say, this decision going into quadrant 2, searching in quadrant 2, maximizes our overall utility. Yeah? So here we are now, Undersea Rescue Command. That's where we need to make the decision. We have many possible decisions to make. So let's now encode that decision part as a Bayesian network again. So I'm initially starting separately, but then we will we will connect both models and use those simultaneously. So at the beginning, top node is the decision node, and the decision choices are no rescue, search in quadrant 1, 2, 3, or 4. So those are our options, and here the cost is very straightforward, because if we do no search, there's no cost associated with a search and rescue mission. If we launch a mission, we have the cost of sending a vessel there and so on. So that's perhaps relatively easy to quantify. Now, what's more difficult to quantify, what are the probability of detection? So, and there we need to take into account, well, if they are in quadrant 1, and quadrant 1 is so deep, and if we were searching in quadrant 1, how probable is, how likely is it that we would find them? And then, of course, if we find them, how probable is it that we rescue them? And then what is the utility of the rescue? So that's kind of the American branch here on the right. On the left, we have the Chinese response. So because we need to assume or need to think about, well, if we were to launch a search and rescue effort, would they notice it? And perhaps in certain areas they wouldn't notice or wouldn't care. But of course, if we were close to their claimed waters, then they would certainly notice and then respond in a certain way, and they would launch their own search effort. Perhaps not search and rescue, but perhaps search and destroy effort. Who knows?
Excuse me?
Yes. Yeah.
In the program, BayesiaLab, do the nodes have a programmatic difference, or are they purely symbolic just to keep the person organized? Because I just always use the circular.
Yes. So here it's a good point, Corey. The circular nodes are the regular nodes that represent a variable, and in this case, either observable or not observable. The square node, that's a decision node, the one at the very top. Let me just go back here. Because that is strictly a node that we have to decide. It's a switch where we say we do this, we do that, we do that. And our objective will be to find the optimal decision. And then the diamond-shaped node, those are utility nodes. They stand for, or they capture what state of, in this case, a parent node, or what's the cost of a certain action. So in this case, we have search and rescue decision is the parent node of a utility node. In the utility node, we would simply say, doing a search and rescue mission is so many dollars. It's right off the bat, it's $100 million, $10 million to launch a vessel into a certain area of the ocean. So those are the new nodes I'm introducing here.
So does the program itself have different rules around using those nodes, or are they the same in the background?
Well, no, they're different. They have different. There are different things you can do with those nodes. They have very different meaning to BayesiaLab. No, it's not. It's just visual. They have very different. Very different roles in the Bayesian network. So continuing on the Chinese path here, we have detection of how likely are they to detect, and then that's the big one, and that's the one I want you to tell me about in our elicitation exercise. How will the Chinese respond? That's the big unknown, where we can't look at procedure manuals and expertise. Now we need to talk to, the Henry Kissingers of the world. What do you think? What are they going to do? And please, no offense to my Chinese friends over there. All strictly hypothetical, fictional. Okay, so on the right we have sort of the American path, and on the left we have the Chinese response. And now we need to put the two models together. On the top is what we observe about the problem domain, or what we infer, what we think happened. And on the bottom is where we have to reason about what will happen as a in response to our decision. So on the top, we perform observational diagnostic inference. We reason backwards from what we observe, or the little things that we observe, back to what may have happened. And then going down, we reason in a causal way what will happen given that we intervene, that we send the vessel into the South China Sea, what's going to go on. Yeah. So, yes?
And this may not matter from a mathematical standpoint, but I would think it very plausible that observing the actions of the Chinese response would inform the observational inference of what is actually happening.
Oh, absolutely. So there could be, and this is definitely a totally incomplete model, because perhaps the Chinese discovered that something happened way before us. So, and we could now have a node that represents basically the Chinese response independently of our own search mission. You know, they may have heard a noise in the ocean.
For example, I would expect all the Chinese submarines in the area to return to port if they suspected something had happened.
Oh, absolutely. They probably
The first indication anyone would have.
absolutely. So that would be, I think, an obvious omission of my model here. You know, that we would, before we even suspect that our boys are not coming home, it's like we would see that the Chinese are doing something. There's Chinese activity. You know, what does that mean? And that would probably, there would have to be an arc from Chinese activity in certain quadrants related back to, did an incident happen? You know? Absolutely. And so as you do build these models, usually one thing leads to another. And the tricky part is, well, how far should you take it? Because this can very quickly become like this never-ending exercise where you build complexity and the experts have to determine, okay, this is what we model, this is what we leave out. Yeah? And so don't get me wrong, even though the use of the tool, the use of BayesiaLab is very, very easy and straightforward. The thinking that has to go into it, into building the structure, that is really hard. You know, there's no technology that can really overcome the difficulty of thinking about a very complex problem domain and extracting the important relationships. Of course, if we had thousands of such incidents that happened, we could learn a model. We could discover such a structure. But here, we're confronted with a new situation. But just to give you a feel, I entered some random dummy data into the model, not dummy data, but just sort of my naive guesses regarding the probabilities. And then I let BayesiaLab look for the optimal solution. And it was really quite interesting how the optimal decision really bounced around. You know, it's day 5, we have received an emergency signal, as opposed to it's day 6, we have not received an emergency signal. And the thing is, there is no intuitive way of arriving at that same conclusion. And sometimes it was really quite bizarre. Like, it would indicate that the optimal decision in one instance might be, given that we heard an emergency signal, we should not search, as opposed to if we did not hear an emergency signal, we should search in a certain place. You know, it seems counterintuitive, but when you trace the signals and the inference, ultimately it's the correct solution given the assumptions. So what I now like to do with you is actually do that, elicit some of these probabilities. And given that we only have 20 minutes left, we obviously can't do the entire network. I mean, this would be hours and hours of probability elicitation. That wouldn't be a lot of fun. So what I'd like to do is just focus on one particular area of the network, the one where it's perhaps least obvious as to what the probability should be. So what I want to elicit from you, what is the probability of the Chinese response? And I have three choices here. No action by the Chinese, a rescue attempt by the Chinese, or capture and a hostile action. So these would be the three possible states. And I would like you to assess these probabilities as a function of three possible territories: Chinese territorial waters, Chinese claimed territorial waters, and international waters. And let me now show you how this works. And I will quickly cycle through the slides and then go back and let you follow along. You would log into the Beaky website, log in with your credentials, and I'll give you your credentials momentarily. You take these credentials, log in, then select the project. First select the account, then select the session. The session is named Submarine. And once you are in that session, then I, from my BayesiaLab installation, will send you assessment tasks. So I will basically open the network and say, instead of me typing in the numbers like I did earlier with the missing bag, I will send that assessment task to you and let you provide your beliefs. And this is what it will look like. You will have an overview page. You will have sliders where you can set the probabilities or type in the probabilities, provide your estimates, and you can provide your confidence level. Perhaps for some of you, you may have China expertise, so you may say, I feel fairly strongly about this. That's how they would react. Perhaps you're retired submarine captain or something, you know. And then you have the ability to add any comments, just like what I said, because if you have domain expertise, you may say, hey, I've sailed the South China Sea. That was my context as I was thinking about this problem. You enter those comments, you click validate, and as you submit your opinions, your ratings, it immediately cascades back into the Bayesian network that I have on my laptop. So you're immediately populating this network, and I see how the feedback is trickling in. And then step by step, we could populate all these tables. Now, doing that in real time is often not practical because there may be dozens of individual assessment tasks that you'd have to go through. So what we typically do is go through, in practical work we do with our clients, we elicit the structure in a workshop, in a brainstorming session, and then at the end of the day, the experts take the probability assessments home as homework. So basically, we would agree on the structure, and then you could, at your own pace, go through the probability assessments. And the next morning, we would continue. All this entire network would be populated with numbers. We could see how it works, and then usually what happens is new issues come up. So, we forgot this. We need to take into account that. And so it's very often an iterative process until we kind of settle on, okay, this is how we think the problem domain works. Okay, let me now just, yes?
Can you talk about how you resolve or combine differences of opinion for the different inputs?
Yes, because we maintain the distribution of responses, or we will actually see how close together the responses are as opposed to how far they are apart. Because that is very important, because if they're very opposing views, then sometimes it may be a misunderstanding that, people, what we often see is when we do work with the Army or the Navy and the Air Force, there are different schools of thoughts between them. So in the responses that come back, we can say, okay, these responses came from the Navy, these came from the Air Force. And then we need to trigger people and say, okay, hold on, think about it. This is the context. Are you sure you're thinking about the right domain? And so on. But that's a very, very important part that and we will visually see that momentarily as your responses come back, how uniform or how much they converge or how much they are apart. And then we can even do a cluster analysis on that. We can then see, are there different schools of thought among the experts? How? So, yes, Bob.
Do you find any system agnostic to cultural background? We're talking about mostly Anglo-Saxon applications here, but if you've got Asians or Europeans or South Americans, do you find any clusters there?
Yeah, absolutely. And that emerges from the responses. There's different kind of the schools of thought, the different cultural backgrounds emerge in the responses, and that's what must prompt the facilitator to address that. Because perhaps like, let's say if you have Germans in the group, like myself, you would immediately think the Germans probably know this very precisely. They've thought about it. They're engineers and so on. So you'd perhaps give them even more, as the facilitator, you'd give them more credit. Give them more confidence. As opposed to the French, yes, thank you. Yeah, but the French, you'd say, what do they know? So yeah, absolutely, because you want to overcome any such, cultural biases that come in that way as much as you can. Of course, you can't perfectly avoid it, but you need to address it as much as you can. But the biggest problem is you can't ultimately validate it against ground truth, because there is no ground truth. All of this is only as good as what we think. This is the best we can do. Okay, so let me just rewind here. And for those of you who have a laptop with them, who's got a laptop with them? Okay, we've got a few. So I would encourage you to log. Well, actually, for those who have a laptop, please keep your hand up. For those who want to participate in the exercise, okay. Corey, you've got a laptop too? Okay, so this will work, yeah. So everybody who's got, leave your hand up, because I will now assign numbers to you. Let's start with you. You're number 2. Corey is 3. You're 4. Chinese gentleman is 5. David is 6. You're participating. 7. 8. Christina is 9. Stephen is 10. And the gentleman on the right is 11. So remember that number, because that is now your login.
Can you repeat the assigned numbers? Because I had my hand raised.
Oh, you had your hand up. Oh, I'm sorry, I didn't see you, Ross. Okay, in that case, you're 12. You're 12. Sorry, I didn't see you. You were hiding behind that counter here. So you're 12. So log into. So the login is here, bkey3.BayesiaLab.com. Then select sign in with Bayesian. And then your credential is bkey, your number, at bayesian.us. So like Stephen would be bkey10 at bayesian.us, and the password is the same for everybody. Quick show of hands, who's logged in? Sui? You're in it? Okay.
Yes.
Okay, so now you have to select the account. Just select the second one, Bayesian USA SG.
I'm sorry, could you repeat the password? The password.
Here, yeah, the password. So in your case would be bkey12 at bayesian.us, and the password is BayesiaLab 6. Yeah, on smaller devices it may be a little bit more tricky. I tried it yesterday and it sort of worked on my iPhone, but obviously a proper laptop is much more convenient. Okay, so then once you've selected the account, you can either double click on the session submarine or highlight it and then click on Go to Submarine, or then click on the Go to icon.
Might say it's closed.
It says it's closed? Oh, okay, well then I need to open it, sorry. I thought I had opened the session. Let me, yeah, no wonder, it is closed. Okay, now it should be open. And now it will say waiting for assessments. Let me just show you what this looks like on my end. So I'll be switching back and forth between PowerPoint and BayesiaLab right now. Let me just leave PowerPoint in the slideshow. And I'm now going into my network, opening the node that I want to elicit, and then highlight the cells that I want to obtain from you. Oh, you can't see that. What is this? Why does this not show my screen? Okay, now you can see my screen again. I think when PowerPoint crashed, it changed something about my settings. So I've opened the node, in this case, plan response. And I'm now selecting the nodes I want to elicit from you. In the conditional probability table, now I say assess and select bkey elicitation. Yeah? So now it is sent out to you, and because I'm delayed or I hadn't already opened the session, you may have to go back into session overview and go into the session again, reselect the session. So, and I now have the overview of all participants as to who has responded or not. And depending on what browser you have, and that's a little bug of our latest release, you may have to tab your way through until you get to the validate button. So if you can see the validate button at the bottom of your submission page, you just need to keep tabbing until you get to that point so you can click validate. Dave, is it working for you?
I'm getting a message you cannot access the session, is not on track. Can't even get the session.
Okay, go back. Everybody go back to the session overview. It probably happened because I logged in after you did. So if you can go back to session overview and then reselect the submarine again.
What did you say to do if there's no validate button?
Excuse me?
When there's no validate button?
Tab. Click on tab, the tab key, and then we'll progress you through the page until you get to the validate button at the bottom. Okay, I've got the response from user 4. Okay, user 3 has responded. I mean, you wouldn't see that. I mean, that's just for the facilitator. I'm just showing you how the facilitator's view of this elicitation process. Importantly, your individual assessments are confidential. So, and that's the whole idea of the Delphi process, so that Christina's overpowering opinion doesn't discourage you from voicing your own beliefs. Okay, given that we only have like 2 minutes left, I will close this elicitation process, obviously before we're all done. I'll just click OK here on my end. And now I have the full list of everybody's responses. You wouldn't see that, but I can now accept that. And that now populates, that feedback will now populate the conditional probability table associated with this node of interest. For each node, it is the arithmetic mean, and this icon. Hold on, let me zoom in. The icon, this is like two people shaking hands. The stronger this is, the stronger the color of this icon is, the stronger the consensus. If it's weak, it's kind of faded out, which means there is less consensus regarding this particular variable or that particular conditional probability.
Okay.
Yeah. So, and now obviously here we just have a few data points, and very few of you had a chance to go through all the assessments, but obviously this would, in a real session, be populated by more data points. And therefore, we could now see really how strong of a consensus do we have between the opinions in the group of experts.
What if you opened up the window really quick and then closed it so you can get distractors?
Say it again, please, Ross.
What if you opened up the window really quickly and then closed it so you could get distractors?
Oh, absolutely. So yeah, of course, that is now could be another bias that I say, okay, minute is up. whoever hasn't turned it in is out. And you want to avoid that. So in the most typical use case would be to say, okay, I'm assigning those elicitation tasks as homework. So instead of me waiting now for everybody to log in and provide the feedback in real time, I would say, okay, take this, take it home, log in on your own schedule, provide the assessments, and by tomorrow morning, all those assessments have come back, and we can then look at the combined results. So that's the typical workflow. As opposed, I just wanted to show you how it works in a live environment, so you can also see what the facilitator's view is of all that. So I'm now accepting that. So you have now defined a portion of this variable that represents the response of the Chinese Navy. So even though you haven't had a chance to assess any of these other nodes, we could take this network now as it is and now look for our optimal decision. Now you simply have to go with all the dummy data or the dummy estimates that I've put in earlier. But we can now use this network saying, given that it is like day 5, we have not received an emergency signal. The sub has not come back. We've not had a report from them. What is the optimal decision? We could now let BayesiaLab search, given the utilities, given the probabilities, and give us compute the optimal decision. So in this case, the optimal decision would be searching in quadrant 2, and here's the associated utility. Now, if it were day 6, and we hadn't heard from the submarine, now it would be a quadrant 2 in which we should search. Now, if we did receive an emergency signal, let's see what happens then. Actually, in that case, it doesn't change. We should still search in quadrant 2. And so on. So I can now try out different scenarios depending on where we are, what we have learned, and then optimize our decision on that basis. Yeah.
Did you use this on the Malaysian airline?
Yes, could be used.
Okay.
Yeah.
I didn't know if they used it.
No, they didn't. No. So, we are pretty much out of time. And I know we kind of, not just are out of time, we ran out of time now towards the end. So please allow me to share some concluding remarks. So, here we go. So you can try this out for yourself. So here are the download links for 2 types of evaluation versions. I actually recommend that you go for the full evaluation, the unrestricted evaluation, because that will give you the full feature set of BayesiaLab. You will automatically receive the network that I just shared with you, and then you can try out all your own scenarios. You can update the probabilities, your assessments, whatever you enter your beliefs, and then try out the optimization on that basis. Now, if you're interested in learning more about Bayesian networks and how to perhaps use them for your application domains, we have regularly scheduled courses around the world, introductory and advanced courses. I just spoke with Karen about the one coming up in Washington, D.C. There will be one in Washington, March 19th through the 21st. Before then, we'll have a course in New York City, in South Africa, in Dubai. We're kind of, each month, we're in another major city around the world. And I would also encourage you to take a look at our website. We have an online community. And much of it, though, is very much focused on the data mining side with BayesiaLab that we didn't talk about at all. We only talked about knowledge elicitation. But that's really just one half of the world of Bayesian networks, because a lot of it is discovering knowledge from data, human-machine teaming in decision-making, and so on. It's a very, very broad spectrum of topics that are being discussed in our online community. We just concluded our annual BayesiaLab conference, well, that is 4 weeks ago in Chicago. And I'm mentioning that because we have video recordings of most of the presentations. You may want to check those out just to see the many different application areas of Bayesian networks, from market research to medical research. It's a broad spectrum. I find it fascinating to see how Bayesian networks are employed all around the world in many different fields. And then looking forward to next year's BayesiaLab conference, I already want to put this onto your calendar now, because this is going to be probably the biggest one yet. We will have our annual conference at the North Carolina Biotechnology Center, October 10th and 11th. We were actually hoping to do it here in this facility, but they don't have room that is big enough for us to accommodate us. So there was, until a few weeks ago, there was a chance that we would actually have our annual conference here. But unfortunately not, we'll be in North Carolina. So with that, I realize I dumped a whole lot of information on you across many different aspects of Bayesian networks. I hope it was useful for you. I would certainly appreciate your time and interest. I have my contact details on the screen. I'd love to continue the conversation with you, speak offline, or if your organization has an interest, perhaps hosting an event similar to this one on your premises with your colleagues, we can certainly talk about that. So with that, thanks again. Have a nice evening.